What if I told you that 4 billion years ago, Mars had flowing rivers, maybe even an ocean, and an atmosphere thick enough to keep water liquid on its surface? Meanwhile, Earth was still getting pummeled by asteroids and had barely any oxygen in its atmosphere. Yet today, Earth is a blue oasis teeming with life, while Mars is a frozen desert where the atmospheric pressure is so low that your blood would literally boil if you stepped outside without a spacesuit. How did these two rocky planets, formed from the same cosmic materials in the same solar system, end up on such different paths? Today, we're going to explore the fascinating forces that shaped these two worlds. Let's get one thing straight, right from the beginning. Mars and Earth were never actually identical twins. They're more like siblings who started with some similarities, but had crucial differences from day one. Both planets formed about 4.5 billion years ago from the same disk of dust and debris swirling around the young sun. Both are rocky planets with similar compositions. Both developed atmospheres through volcanic outgassing, and both had liquid water on their surfaces during their early histories. But here's where the similarities end and the crucial differences begin. First, Mars is significantly smaller than Earth. With only about 11% of Earth's mass and 53% of its diameter, Mars has always been the smaller sibling. This size difference affects everything, from how long the planet stays geologically active to how strong its gravitational pull is. Mars orbits much farther from the Sun, while Earth sits in the comfortable middle of what astronomers call the habitable zone. Mars is right at the outer edge. It receives less than half the solar energy that Earth gets, making it inherently colder and requiring a much thicker atmosphere to maintain liquid water on its surface. Mars likely had a much shorter window of geological activity. Smaller planets cool down faster, which means Mars's volcanoes probably went quiet much earlier than Earth's, cutting off the supply of greenhouse gases needed to maintain a warm climate. These weren't random accidents or cosmic bad luck. They were the inevitable consequences of Mars's physical characteristics interacting with the laws of physics over geological timescales. One of the most significant differences between modern Earth and Mars is that Earth has a strong magnetic field, while Mars has virtually none. But understanding why requires diving into what's happening deep inside these planets. Earth's magnetic field is generated by our planet's liquid outer core, where molten iron flows in complex patterns driven by the planet's rotation and internal heat. These moving electrical conductors create the magnetic field that extends far into space, forming what scientists call the magnetosphere. Mars once had a magnetic field too, but it disappeared early in the planet's history. The leading theory is that Mars's smaller size meant its interior cooled much faster than Earth's. When the core cooled below a critical temperature, the convection currents that generated the magnetic field simply stopped. Without this magnetic shield, Mars became vulnerable to the solar wind, a stream of charged particles constantly flowing out from the sun. Over millions of years, this solar wind gradually stripped away Mars's upper atmosphere, molecule by molecule. But here's what's important to understand. The loss of Mars's magnetic field wasn't the single cause of its transformation. It was one factor in a complex web of processes that all reinforced each other. As the atmosphere thinned, the planet got colder. As it got colder, more water froze. As more water froze, there was less water vapor in the atmosphere to trap heat. Each change made the next change more likely. Earth's stronger gravity helps us hold onto our atmosphere, even when the solar wind tries to strip it away. Our magnetic field deflects most of the solar wind, but even without it, Earth would lose atmosphere much more slowly than Mars did because of our stronger gravitational pull. Mars, with its weaker gravity and no magnetic field protection, began losing its atmosphere relatively quickly in geological terms. But the process was gradual and complex, not the simple linear progression that's often described. As the atmospheric pressure dropped, liquid water became unstable on Mars's surface. Water can only exist as a liquid within a specific range of temperature and pressure conditions. As Mars's atmosphere thinned and its climate cooled, most of the planet's surface moved outside that range. Some of Mars's water escaped to space as vapor. Some froze into permanent ice deposits. Some may have been absorbed into the planet's crust. The result was a planet that transitioned from potentially habitable to definitively hostile to surface life. Earth avoided Mars' fate through a combination of advantageous characteristics and self-reinforcing systems that developed over time. Our planet's larger size means our interior is still hot and active today. This ongoing geological activity does several crucial things. It maintains our magnetic field, it recycles carbon through volcanic emissions, and it regulates our planet's temperature through the carbon cycle. When Earth gets too hot, chemical weathering increases, pulling more CO2 out of the atmosphere. When it gets too cold, volcanic activity adds more CO2, warming things up. It's not perfect, but it's been remarkably effective at keeping Earth's climate within the range where liquid water can exist. Our distance from the sun also puts us in a sweet spot where we receive enough energy to maintain liquid water, but not so much that we risk a runaway greenhouse effect, like what happened to Venus. The Moon, formed early in Earth's history through a massive collision, provides additional stability by preventing extreme variations in Earth's axial tilt. While Mars's tilt can vary wildly over long periods, Earth's remains relatively stable, preventing extreme climate swings. Here's where Earth's story gets really interesting. Once life appeared on our planet, it began actively participating in maintaining the conditions that allow life to continue. Photosynthetic organisms produce oxygen and absorb CO2. Ocean organisms affect cloud formation and atmospheric chemistry. Even the soil microbes play roles in global chemical cycles. Life on Earth doesn't just passively experience our planet's environment, it actively shapes it. Mars never developed this biological feedback system. Without life to help buffer environmental changes, Mars had no mechanism to recover from the atmospheric and climatic shifts it experienced. This doesn't mean life caused Earth to be habitable. Earth had to be habitable first for life to develop. But once it appeared, life became part of the system that maintains Earth's habitability. While magnetic fields, atmospheric retention, and geological activity all played essential roles in these planets' different evolutionary paths, the fundamental driver might be the most obvious one: their distance from the Sun. Mars receives only 43% of the solar energy that Earth gets. This means that to maintain the same surface temperatures, Mars would need a much thicker atmosphere with more greenhouse gases than Earth has ever had. During Mars's early history, when it had a thicker atmosphere and active volcanoes pumping out CO2, it might have been warm enough for liquid water. However, this was always a delicate balance that became increasingly difficult to maintain as the planet's geological activity declined and its atmosphere was gradually lost to space. Earth, sitting closer to the Sun, has more energy to work with and doesn't need as thick an atmosphere to maintain comfortable temperatures. This makes our climate system more resilient to changes. The different paths that Earth and Mars took aren't unique or surprising. They're examples of how planetary systems naturally evolve based on their physical characteristics and environmental conditions. Smaller planets tend to cool faster and lose their atmospheres more easily. Planets farther from their star need thicker atmospheres to maintain liquid water. Planets without magnetic fields are more susceptible to atmospheric loss. These aren't mysteries. They're predictable consequences of well-understood physical processes. What makes Earth special isn't that we won some cosmic lottery, but that we happen to have the right combination of size, composition, distance from the sun, and evolutionary history to maintain conditions suitable for life as we know it. Scientists are actively searching for evidence that life might have existed on Mars during its warmer, wetter period billions of years ago. Recent missions have found organic compounds and seasonal methane emissions that could indicate past or even present microbial life. If life did exist on early Mars, studying it could teach us enormous amounts about how life develops and adapts to changing planetary conditions. It might even help us understand the range of environments where life can persist. The comparison between Earth and Mars offers profound insights into how planetary systems work and what factors determine whether a world can support life. Earth's habitability results from a complex interplay of factors, including our size, distance from the sun, magnetic field, geological activity, atmospheric composition, and the eventual development of life itself. Change any one of these significantly, and our planet's history could have been very different. Mars shows us what can happen when some of these factors are different. Its smaller size, greater distance from the sun, and earlier loss of geological activity led to the gradual transformation from a potentially habitable world to the frozen desert we see today. Both planets are natural laboratories that help us understand the conditions necessary for habitability and the processes that can threaten or preserve those conditions over geological time. This understanding becomes increasingly important as we discover thousands of planets orbiting other stars and try to determine which ones might be capable of supporting life. The story of Mars and Earth isn't just about our solar system. It's about the fundamental principles that govern planetary habitability throughout the universe. Understanding these principles helps us appreciate both the remarkable nature of Earth's life-supporting environment and the scientific processes that created and maintain it. We're not just living on a lucky planet. We're living on a world whose habitability is the result of billions of years of complex, interconnected processes that continue to operate today.